Okay, I'll get started. I wanted to begin with an announcement about test one that's coming up not next week, but the Tuesday of the following week. So test one will be in our regular class time. Test one will be on Zoom, and I'll administer test one as a Canvas quiz or Canvas test. It will have multiple choice questions on the test. The lecture quizzes are intended to be practice for that. It'll have some numerical answer questions on the test. WebAssign homeworks are meant to be practice for that. And it will have one fully worked out problem on the test. The recitation problem that you submit is meant to be practice for that. If you want to look at some old tests of mine, of course, they're not Canvas tests, but you might want to look at them for the style or the content. They're in our Canvas course. And there's also an equation sheet that you can use during the test that's posted on our Canvas page. The test one, so it's Tuesday, September 15th, is going to cover the material that we've covered in the 8 lectures up to that test. So it's going to cover our work on kinematics that was describing motion in 1 and 2 dimensions. And it's going to cover our upcoming work on dynamics. It's understanding, explaining motion in 1 and 2 dimensions. It's Newton's laws of motion. And so that's the material for the first test. It's from chapters 1 through 4 of the textbook, and the specific content is listed in the syllabus and is listed on this overhead. Any questions on all that? Let me put the chat on. I've lost the chat here. Okay, I don't see any questions right now. If you have some questions, you might want to put them in chat. I can answer them at the end of the lecture if they're about the test rather than about the content of the class today. Okay, so I'm going to get on with today's lecture. So we're making a transition today. We're moving from our work on what we call kinematics, the description of motion, to what we call dynamics, the explanation, understanding of motion. So in kinematics, we looked at, falling bodies and projectiles as examples of one-dimensional and two-dimensional motion, and we learned how to describe that motion. In dynamics, we're going to look at, again, falling bodies and projectiles as examples of one- and two-dimensional motion, but we're going to explain more deeply that motion. So that's the overall theme of the next few lectures. Specifically today's content. So I want to tell you how forces, so forces are like pushes or pulls, how they are the phenomena or the quantity that cause objects to, for example, speed up or slow down or change their directions. So forces are key to explaining, understanding motion. I want to introduce Newton's laws of motion. And Newton's laws of motion really describe how these forces, quantitatively, how these forces alter or change the motion of an object. And so those really make concrete and quantitative the explanation of how these forces act to change the motion, speed up, slow down, change the direction of an object. And then we'll introduce some everyday forces. We'll talk a bit about gravity, a little bit about friction, a little bit about contact forces, and look at some examples involving these everyday forces that we experience in our everyday world and how they influence motion. The next two classes next week will be much more work on applying Newton's laws to everyday forces to understand the motion of everyday objects. So today's examples will just be a beginning, a start of that work. Okay, so as I mentioned, forces are, forces are a word you're familiar with. Forces in physics are things like pushes, things like pulls that are illustrated here. So there's a few important remarks about forces that I should make when I get my annotation going. And I've gone to the wrong slide now. By the end of the semester, I should be able to get control of this. I'm hoping. Okay, so forces have both size and direction. So a force might be a large force or a small force, a strong force or a weak force. And a force might be a force to the right, or a force that's upwards, or a force to the left, or a force that's downwards. So they have both size and direction. So that means that forces are vectors. Just like we met displacement, which was a vector, it has size and direction. Velocity was a vector, it has size and direction. Acceleration was a vector, it has size and direction. So those are other examples of forces. Forces, the key thing about forces is that the action of forces, the influence of forces, is what alters motion, is what changes motion. And that's what today's class is about. Okay, so on this slide, on the upper panel, I'm picturing what I might call everyday forces. The forces that we see in our everyday experience. And on the bottom panel down here, I'm picturing what we would call fundamental forces, what we would see at a deeper level. So let me just work through this slide a little bit. So everyday forces are, as I say, are things like pushes and pulls. So look, here I am pulling on this handle on this spring. And that force that I exert is something we would call a contact force. I'm in contact with the handle of the spring. My friend here, right, is pulling this cart, pulling the handle of this cart and exerting a force, what we would again call a contact force. And then here I am, I'm playing football and I'm kicking the football. And when I kick the football, I exert a force on the football. That's a contact force too. And so in our everyday lives, as we push, pull things, as we sit down, as we walk around, we're experiencing contact forces. And these are our everyday forces. At a deeper level, the forces of nature, the fundamental forces of nature, we'll discover are, for our purposes, these four forces here. There's gravity, that's a fundamental force of nature, down here on the bottom left. And it's a force that acts between pairs of masses, between two masses. And then there's electric forces in the center downstairs here. And that's a force between electric charges, between pairs of electric charges. And then another force you'll meet in general physics is magnetic forces. And that's a force, for example, between magnets. And so these three forces, gravity, electricity, magnetism, they are fundamental forces. They sort of underlie or are the sort of foundations, the cornerstones of these more everyday forces that we experience in our everyday lives. But it's important that if you look at all these forces in each of these six pictures, I'm picturing the force as an arrow, meaning I'm picturing the force as a quantity that has both size and direction. The arrow length describes the strength of the force, the direction of the arrow, the direction of the force. And all of these pictures here involve a force arrow, a force of a certain strength and a certain direction, a force of a certain strength and a certain direction. And likewise down here for the fundamental force of gravity, the fundamental force of electricity, the fundamental magnetic force. The forces are vectors with sizes and directions. Okay, let me make a remark about gravity, electricity, and magnetism. Because they have an interesting feature that we call action at a distance. So when there's a gravitational force between two masses, it acts over some distance, over some empty space. The two masses don't have to be in contact. When you have electric force between two charges, it acts over some distance. The two charges don't have to be in contact. When you have a magnetic force between two magnets, it acts over some distance. The two magnets don't have to be in contact. That's at odds with those everyday forces, like kicking, when I kicked the football, when I pulled on the door handle. I was in contact with the football. My foot was. I was in contact with the door handle. My hand was. Those were contact forces. And this really puzzled Newton and other scientists because they felt this action at a distance of the gravitational, electrical, magnetic forces was very mysterious. How could gravity, electricity, magnetism act over empty space, act over that distance? So later on, it turned out, it was found out, and you'll discover this as you work through general physics, that these action at a distance forces like gravity, electricity, and magnetism, they're actually carried through empty space by what we call force fields. You can't see these force fields, you can't taste these force fields, but they're carried through space by force fields. And so the gravitational force between two masses is carried by a gravitational field. The electric force between two charges is carried by an electric field. Magnetic force between two magnets is carried by a magnetic field. And these are real things, real fields. We can't see them, we can't taste them, we can't smell them, we can't hear them, but they are real. And what's interesting is actually that if you were to shrink down to the scale of the atoms and the molecules of the materials in our everyday lives, those everyday contact forces, like me pulling on the handle of the door or me kicking the football, those are actually at the atomic molecular level, action at a distance electric forces. And so that's what I meant by, that's what I hinted at, that these fundamental forces, like the electrical force, underlie are the foundations of the everyday forces, like like contact forces, like friction forces, like tension forces. Okay, so now let me just, on this slide, list Newton's 3 laws of motion. And then we're going to spend many more slides just looking at these laws of motion in detail. So this is just a summary of the 3 laws of motion that ultimately describe how forces influence, affect motion. So the first of the 3 laws. So it's an interesting one, and it's actually a statement, quantitative statement, describing how things move when there is no force acting on the object. So it first tells you, Newton's laws first tell you what happens when there is no force acting on an object. And an example of that might be, supposing you had a space rocket. I'm in a space rocket and I'm in deep space, far from the Earth, the sun, or whatever. Out there in deep space, no forces are acting on me and my space rocket. And Newton's first law describes that situation. Second law then picks up the story and describes quantitatively, makes a quantitative statement about how things move in the presence of a force. That is, how a force will influence or affect or change the motion of an object. And that's the second law. An example of that might be, when I went into outer space, deep space in my space rocket, I had to leave Earth to get to outer space in my space rocket. I had to blast off from Earth to get into deep space. And during that event where I left Earth, there were forces acting, which changed my motion and got me into deep space. So the space rocket blast off is an example of the Newton's second law of motion. Well, third law of motion is an interesting one. So the first law tells you how things move when there are no forces. Second one, how things move when there is a force on the object. Third one is sort of a corollary to that. It describes the fact that whenever an object exerts a force on some other object, that other object exerts an equal-sized, opposite-directed force back on the first object. It says that forces always come in pairs. Like couples always come in pairs. Well, forces always come in pairs too. But with forces, those that come in pairs, those two forces are closely, specifically related to one another. Anyway, these are the 3 laws that we're going to talk about. First law, second law, and third law. And so let's move on with doing that. Let's start with Newton's first law. It's actually called the law of inertia. Often you'll hear it called the law of inertia. And so we'll also say not only what Newton's first law is, but what inertia actually is. So here's a statement of the law. This is Newton over here on the right, and this is what he said. He said that an object will remain at rest if it's initially at rest, or an object will move with constant velocity if it's initially moving, unless forces act. So this is a statement about the situation for objects if there are no forces acting. And it's just saying that, if there's no forces acting on an object, if it was at rest, it's going to stay at rest. If it was moving, it's going to stay moving with the same velocity. i.e., if no forces act, there's no change in the motion, or if it was at rest, there's no change in it being stationary. So it's that special case, and it's an important special case. Now, you might think, well, look, that's not true. I was riding my bike to school today, and if I stop pedaling my bike comes to a stop. If I stop exerting a force on the pedals, my bike changes its motion. Me and my bike come to a stop. I was driving to school today. And I might say, well, if I stop putting my foot on the car's accelerator, exerting a force on the car's accelerator, then the car comes to a stop. It seems from our everyday experience, riding the bike, driving the car, that we need to exert a force to keep ourselves in motion. And so it seems this law can't be true. It seems this law can't be right. But it is true, it is right. And I want to show you a demonstration of that. The reason that the bike comes to a stop if you stop pushing on the pedals is because you've not removed all the forces. You've removed your force, but there's still frictional forces that slow and stop the bike. Likewise, the reason the car comes to a stop is that when you take your foot off the accelerator, you've stopped the force propelling the car forward from the engine, but you've not removed all the forces. There's still frictional forces that will slow the car down and bring the car to a stop. And so it's actually very hard for us. It's very difficult for us to, in our everyday lives, in our everyday world, see the case that Newton is talking about in this first law. See this case where there are no forces acting on an object. When the car is slowing down, frictional forces are slowing it down. When the bike is slowing down, frictional forces are slowing the bike down. And so I want to show you a demonstration where we're going to strip away the frictional forces. So I'm going to share a different screen. Okay, so I can hope you can see a second screen where I've made a little video. It's pretty low budget, I'm afraid, but we're going to demonstrate the fact that in the absence of forces, an object will continue moving with the same velocity. Its motion won't change, and that's Newton's first law. And I'm going to demonstrate it with this device that we call the air track. I'm going to push a cart on an air track, and the air track, when activated, the car floats on a cushion of air, and that removes the frictional forces. And so unlike, stopping pedaling the bike or taking your foot off the accelerator of the car, where you couldn't remove the frictional forces, for the cart and the air track, we can remove the frictional forces. And so we're just going to watch that. And so I push the cart to the right, and it just slides to the right. And then it bounces back to the left, and it bounces back to the right again. And it bounces back to the left again. Now I'm going to stop this, and I'm going to put it in slow motion. And I'm going to just make a couple of comments. So when you watch it traveling from the left to the right, or from the right to the left, during that period, we've removed the frictional forces. It's floating on this bed of air, this thin film of air. And what you're seeing is that it's not changing its motion. It's neither speeding up nor slowing down because there's no forces acting on it. Now, when it gets to the right-hand end of the air track or the left-hand end of the air track, well, there's a bumper at the left-hand and the right-hand end of the air track, and the car bounces off. So there are forces that change the motion. But we're talking about that gliding, constant velocity motion from the left bumper to the right bumper or the right bumper to the left bumper. And there you want to focus on the cart moving with the same constant velocity. So let me just slow it down a bit. And as it traveled across to the right there, it just moved at constant speed. Across to the left, it's just moving at constant speed. Back across to the right, it's moving at constant speed. and then we'll see back across to the left again. It's moving at constant speed. Now, each time it goes backwards and forwards and backwards and forwards, it's going slower, you'll notice. That's because of the bouncing off the right bumper or the left bumper. But during the transit between the bumpers, from left to right or right to left, its velocity is constant. On the movie, it actually looks a little jittery, and that's just the movie. But it is, if we were in the, I missed the lecture room now. If we were in the lecture room, this motion would seem so smooth, so elegant. It would really be a wonderful thing to see. I guarantee you. Okay. So that was an example of Newton's first law. Let me unshare that screen and then reshare my slides. And let's move to the next slide. And on this slide, I want to say something about this word inertia, what we mean by inertia. What is inertia? So actually, it was Galileo 100 years before Newton that cultivated the idea of inertia. And what he thought about inertia was that anything that has mass, anything made of matter, so you and I, for example, or my dog here, anything that has mass or matter has a property that we call inertia, a characteristic that we call inertia, and it's that inertia that opposes changes in its motion. It's kind of a resistance to changes in its motion. So in the absence of external influences, that Newton called forces, in the absence of external influence, because of an object's inertia, it will continue to move it with the same velocity that it started moving with. So it won't speed up, it won't slow down, it won't change its direction. Something must influence that matter. Something must push it, something must pull it in order for its motion to change, its velocity to change. And so Galileo really was at the roots of this, this first law of motion. Newton elaborated on it. So what he did was make this clear statement that if an object is stationary, it'll stay stationary. If it's moving, it will stay moving with the same velocity, unless this influence he called a force acts. So that was a more quantitative, more accurate statement. And there's an important point here. What will change the motion of an object, what will order the motion of the object, speed it up, slow it down, change its direction, is what we call a net force. Now, a net force just means the sum of all the forces acting on the object, the resulting force that's acting on the object from all the individual forces that are acting on the object. So one situation where an object won't change its motion is where no forces whatsoever are acting on it. But another situation is where there might be a pair of forces, but they add up to make no net force. They add up to make zero force because they're vectors. Or you might have 1,000 forces acting on an object, but they all add up. Those vector forces add up to make no net force acting on the object. Then again, the object would move with the same constant velocity that it started with. Or if it was stationary, it would stay stationary as it started. Okay, so, a classic example of inertia. Remember, I got in my space rocket. I blasted off from Earth, and now I'm in outer space. And in outer space, I don't feel the gravitational pulls or pushes of the sun or the Earth or the moon. I'm in deep space. In deep space, my inertia, my space rocket's inertia, due to its mass, due to the matter, will we'll keep it moving with the same constant velocity. And we think of that inertia, that mass, that amount of matter as this kind of measure of the resistance to having the rocket's motion or my motion changed. And we think of forces as these quantities or these agents that can change the motion of an object. And so that's a deep understanding of motion, what causes motion, that's embedded in Newton's first law. Okay, I want to show another movie that also shows inertia. And you've seen this famous trick where, you know, you have the wine bottle and the wine glass or whatever sitting on the table. They're sitting on the tablecloth on the table. And you pull the tablecloth out from beneath the wine bottle and the wine glass, and the wine bottle and the wine glass just sit there. And that's because of inertia. They were at rest. You quickly pulled away the tablecloth. They stayed at rest. You pulled away the tablecloth such that you exerted no forces on the wine bottle and the wine glass. And so they stayed on the table. They didn't fall onto the floor. And so we're just going to watch an example of that. So I'm going to share another screen again with a little movie. And this one's actually a BMW advert for motorcycles. And it's a BMW advert for motorcycles that actually even makes me, somebody would be normally very scared of getting on a motorcycle, actually want one. But let's play this. Okay, that was kind of fun. It makes me want to have a soundtrack on my air track videos next time, so I'm going to attempt that. But it was an example of inertia. You pull the tablecloth away, and the objects that are sitting on the tablecloth remain in place because of their inertia, their resistance, their reluctance to being moved. They will only move if a force, net force, acts on them. And by quickly pulling the tablecloth away from beneath them, no net force acted on them, and they just stayed where they were. Okay, so let me go back and stop sharing this one and reshare my slides. And start talking about the second law of motion. And this sometimes is called the law of acceleration. At least I think it's called the law of acceleration, or maybe it's just me that calls it the law of acceleration, but it is about acceleration. So this is Newton again over here on the right, and in words, the law says that the rate of change of the velocity. So if you're changing the velocity, you are changing the motion. And the rate of change of velocity is acceleration, if you remember. The rate of change of the velocity of an object is equal to the force that acts on the object divided by the object's mass or object's inertia. So now this is interesting. First law is a quantitative statement about the case when there no forces were acting and there was no change in motion. Now this is a quantitative statement about when there are forces acting and there is change in motion. And firstly, it's saying that forces change the motion, they change the velocity, and it's saying also how much they change the motion, change the velocity, and it depends on the object's inertia or the object's mass. Now, we normally think of this law not as that statement, but as an equation, that acceleration is equal to force divided by mass. There's a little formula, here it is. The acceleration A is equal to the force F divided by the mass M. It's a little, tiny little, innocent looking law, but it was a massive, a humongous breakthrough in understanding motion. And it's important to recognize that, sort of appreciate that. So it's also important to recognize and appreciate, exactly what these quantities are, the A, the F, the M. So again, let's just walk through them. Mass, that's this measure of inertia. Something with lots of mass has lots of resistance to having its motion changed. An elephant has a lot of inertia. Something with a small mass has not so much resistance to having its motion changed. A mouse has small inertia. The force, that's the agent that causes the change, the influence that causes the change. It causes the speeding up, the slowing down, and the change in direction. And it's what we in our everyday lives think of as a force, as being a push or a pull. And then finally, that combination of force and inertia create a visible, observable, measurable change in motion, and that's the acceleration. The acceleration measures the speeding up, the slowing down, or the change in direction. And that's Newton's second law. And that's why it's a law of acceleration. It tells us how the motion changes in terms of the influence, the force, and the inertia, mass of the object. Okay, a few comments on it on these next couple of slides. First comment is that it's a comment about units. So, we're introducing this new quantity here, force, and we're relating it to older quantities that we got used to. Mass as a measure of the amount of matter, a fundamental dimension of nature with units of kilograms, and acceleration as a basic quantity describing motion, with dimensions that involve length and time and units of meters per second squared. And so we can, based on dimensional analysis, right, that all physics equations, no matter what physics equation, they must be dimensionally correct. They must have the same dimensions on the left and right-hand sides. We can figure the dimensions of force. And if you figure the dimensions of force, they're, a combination of the dimensions of mass and length and time. In units, so kilograms, in SI units, kilograms, meters per second squared. And we use that combinations so much. The concept of force is so important that we call that combination a Newton. 1 kilogram meter per second squared is 1 Newton. And we give it the symbol uppercase N. So this is a Newton here. So that's an important point about the dimensions. Second important point is about these three quantities in Newton's second law, and it involves both vectors and scalars. So mass is a scalar quantity. So the mass or inertia of an object, which measures the amount of matter, is just a size. It's just 1 kilogram or 10 kilograms or 1,000 kilograms. It doesn't have a direction to it, up or down or left or right. On the other hand, the force that changes the motion, that does have both a size, a strength, and a direction, an orientation. And the acceleration that change in motion also has both a size, a large acceleration, a small acceleration, and a direction, an orientation. And you can see here, you know, as a mathematical fact, right, you can take a vector and multiply it and divide it by a scalar and get another vector. And that mathematically is what this equation is about. You see, most importantly, that the acceleration will inherit the direction of the force. So if the force is upwards, the acceleration will be upwards. It inherited that influence, that upwards push. And if the force was to the right, the acceleration would be to the right. It would inherit that direction of the force. Now, one remark about Newton's second law, and it's also really a remark about Newton's first law, is that in the statements that the second law tells you how forces change the motion, or that in the absence of forces for the first law, that there is no change in motion, the force in those laws is actually the net force, meaning it's the sum of all the forces that are acting. It's the total force, the resultant force that goes into Newton's second law or Newton's first law. It's not a particular individual force. So you often will see this, faced with a situation where you have a collection of forces acting, and you have to add those forces up to determine the acceleration or determine the absence of acceleration. And so in this little example here, this is me, my kids were younger. What causes me to fall over is the net force that's exerted by these two pushes and pulls that are acting on me. Okay, let's do a demonstration of the second law of motion now. So as I say, this is a relationship between forces and acceleration and mass. And so we want to explore a little bit that relation between forces, acceleration, and mass. And so I'm going to do this with what we call repulsion carts. And I got a little video of this, just short video. No music to make it dramatic. I'm going to do that next time. These videos are going to be so much better now. I've seen the BMW video. So I'm going to share a different screen again. Okay, so I hope you can see my twin brother standing in the, who also teaches here, standing in the chemistry physics large lecture room, and in his hands are two repulsion carts in red. And we're going to place these two carts on the bench, touching one another. And for the purposes of this demonstration, we want to think of it that there's two carts and there's a spring between them. And when I place them on the bench, I'm going to compress the spring, and then I'm going to release the spring. And the spring is the force. It's the push or the pull. And so both carts get pushed by the two ends of the spring. The one on the left will be pushed towards the left by the left-hand end of the spring. The one on the right will be pushed towards the right by the right-hand end of the spring. So they get equal size pushes, but in opposite directions, to the left and the right. So remembering that forces have sizes, strengths. The strengths here are going to be the same. Also have directions. There's two forces here from the spring. They're in opposite directions. Well, the carts were at rest. We unlock the spring. It exerts its forces. That's going to create motion. And we're going to see at that moment the carts accelerate and then move off with some velocity after that short, almost instantaneous period of acceleration. So let's watch this. And I think I'm going to put this on slow motion. Oh, it is on slow motion. That's good. Kind of looks a little creepy on slow motion, actually, some of it. But I mean, it'll be very helpful when we watch the carts move. And so that was the spring that I loaded between the two carts. And now I'm going to release the spring. So at that moment, I release the spring. There's this short burst of force that's exerted to the left on the left-hand cart, to the right on the right-hand cart. And that causes the carts to change their motion. They were at rest, they get moving. They've accelerated, they're then moving. And then after that short, sharp burst that lasts a tiny fraction of a second, they just move with constant velocity over to the left or right for the left and right cars. And you see that moving away with that velocity that they acquired by the influence or the action of that force. So it's a nice demonstration of Newton's second law and how forces generate changes in motion. Forces cause changes in motion. The carts were at rest, then they were moving. Now, in the next demonstration in this video, I'm going to replay it, but I'm going to double the mass of one of the carts. And if I double the mass of one of the carts, I'm doubling the inertia of that car. If I double the inertia, when the same forces act, well, I'll get different accelerations. The spring will exert the same forces on the left and right-hand carts, but the acceleration will be larger on the cart with less mass, less inertia. It will be smaller on the cart with more mass, more inertia. And for this case, where I've got one cart with half the mass of the other, or one cart with twice the mass of the other, then the accelerations will be twice as big or half as big, depending on what cart you're thinking of. And so the velocities that are required will be half as big or twice as big. So let's just watch that. So I'm going to add to the right-hand cart here a second cart, and they're all identical carts. So I'm doubling the mass of the right-hand cart arrangement compared to the left-hand cart. And then I'll release the spring. And you see here at this moment, the fact that the left-hand cart with half the inertia has moved away at twice the speed. The right-hand cart with twice the inertia has moved away with half the speed. And that's what Newton's second law is telling us, that the force on an object will create an acceleration of the object, but the size of the acceleration depends on the object's resistance to having its motion changed, its inertia, its mass, the amount of matter. And so we're seeing that there. Okay. Let's stop that little guy. And what am I doing next? I'm losing myself. Let's look at an example of Newton's second law of motion. It's going to be of using it, of applying it quantitatively. And here's the question. And I'm going to go through this pretty quickly because it's not a complicated problem. We're going to look at much more complicated problems, you'll be pleased to hear, in the next two classes. But this is a simpler problem. So we're told in this problem, if I can get my annotation going, that will only take me half an hour, so don't worry about it. Here we are. Here's the question. 1,200 kilogram car decelerates from 30 meters per second to rest in 6 seconds. What force was exerted by the road on the car? Okay, first thing to realize here is that there must have been a force exerted by the road on the car. Because if you're going to change the motion of the car, then there must have been a force changing it, and it comes from the road. So that's the important conceptual idea behind this. And then we've got to solve the problem. And we're actually going to solve it in two steps. The first step is that we're going to figure out the force, we actually first need to figure out the acceleration or the deceleration. And so the first part of this problem is a little bit of kinematics that we've done over the past weeks, and we kind of learned to love it. And then the second part is our new love, right, for dynamics in trying to understand forces. So let's take a look at the solution here. And here it is, the whole thing. So the first thing I would naturally do, I always encourage this, it's always really helpful. It's helpful for the physics problem. It's also sort of therapeutically helpful, I think, to make a sketch of what's going on. So here, this arrow represents the motion of the car from where it started to where it ended up. We were told some facts. The car's mass is 1,200 kilograms. That's a fact about the car. Then we were told some facts about the motion. So it started at 30 meters per second, initial velocity. It ended up 0, final velocity. And that all took 6 seconds. And so those are the sort of description of the motion of the car, the deceleration of the car. And so the first thing I'm going to do is actually calculate the deceleration. And to do that, I just use the definition of acceleration that we met some classes ago. And then once I've got the acceleration, I can apply Newton's second law to find the force. So, you know, it's pretty straightforward 2 steps here. And let's just walk through them quickly. So the acceleration, if you remember the definition, it's the change in velocity divided by the elapsed time. The change in velocity is the final minus the initial velocity. So it's 0 minus 30 meters per second. And the elapsed time, how long the car took to stop, it was 6 seconds, we were told. And so I've got minus 30 over 6. Even I know without a calculator that this is minus 5 meters per second squared. That's the acceleration. And that's a vector. It has both a size and it has a direction to it. Now I can calculate the force, which is also a vector. The force that was needed to cause that deceleration, acceleration, is by Newton's second law. Remember, acceleration is force over mass, or force equals mass times acceleration. In fact, this is the way you most often see Newton's second law, rather than A equals F over M. Anyway, the mass I know, I stick in the mass, 1,200 kilograms. The acceleration I know is minus 5 meters per second squared. Multiply those two. Even I can do this one in my head, right? 1,200 times 5, that's 6,000. It's minus 6,000 newtons. Again, this force has both the strength, 6,000 newtons, and a direction indicated by the minus sign. In fact, look at these two minus signs. I had called the direction towards the right in my picture the positive direction. And I did that, you can see I did that because I called V0 plus 30 meters per second. We then found out that the forces are in the opposite direction. The forces and the accelerations are towards the left. And so that's important to understand, that to slow down the car and stop the car, it must be accelerating in a direction that's opposite the motion. And the force that's acting to slow it down must be acting in that direction opposite the motion. That's how you slow down. If the force and the acceleration were in the same direction of the motion, the car would speed up. So slowing down, forces act opposite the direction of motion. Speeding up, forces act in the direction of motion. Okay, well, that was fun. Newton's second law. there's another example here, but I'm not going to go through it right now. I'll maybe add a little video of me solving it on a whiteboard so that you can take a look at that. I've done that with some problems in the on our Canvas page in our modules direction. But I really want to get on to Newton's third law. So Newton's third law is kind of sort of the oddball law, sort of an intriguing law. So imagine two objects that are exerting, well, one of them is exerting a force on the other one. Maybe this is two masses, right? Like the Earth and me. Earth's gravitationally pulling on me. What Newton's third law says is that when object one exerts a force on object two always exerts an equal size, oppositely directed force back on object one. So the example is that if the Earth exerts a force on me, pulling me downwards, that sounds very natural. You know what? I'm actually exerting a force on the Earth. And my force on the Earth is just as strong. It's just I'm pulling the Earth up. So we're stronger than we think. The Earth is not just pulling us down towards the center of the Earth, but we're pulling the Earth up, and we're pulling as hard up as the Earth is pulling us down. That's a remarkable thing to imagine. So forces, not just gravitational forces, all forces come in these pairs, and it's called action and reaction. And I want to show you a little demonstration of action and reaction. And I'm going to show it with the repulsion cards again. So let me share the video of the repulsion cards one more time. Okay, so I'm back in chemistry physics with my pair of repulsion cards. And I want to tell you a little bit more detail about the repulsion cards. It's one of them that has the spring. This one on the left has the spring, and the other one didn't have the spring. And so the way we're going to think about the situation this time, as we watch the cards sitting on the bench and then release the spring and they fly apart, is that the repulsion card on the left-hand side, the one with the spring, exerts a force on the one on the right. And then the one on the right exerts an equal size, oppositely directed force back on the one on the left. So that there's a force pair here, an action and a reaction pair here. That's just like the Earth exerting a force on me and me exerting a force on the Earth, or the Earth exerting a force on you and you exerting a force on the Earth. This is a spring force, not a gravitational force, but still there's a force pair, action and reaction pair. And so when if the cards are equal masses, that action and reaction pair will push the cards, and the cards that acquire equal size velocities due to equal size accelerations, due to equal size forces in the pair, but they'll be in opposite directions. If one's to the right, the other's to the left. And so that's demonstration is also an example of Newton's third law and forces coming in pairs. And it's an important feature of the laws of motion that for every force, there is a partner force. They're always couples. They're never singles. Okay, stop sharing that. And start sharing my slides again. Okay, I want to look at an example of the third law. I'm not going to calculate any numbers here, but I am going to illustrate the third law. So imagine you're holding a ball in your hand. Simple situation. We're going to figure out the forces that are acting on the ball and all the action-reaction pairs involving those forces. And then the second part of the problem, we're going to drop the ball. And as the ball is falling, we're going to consider the forces that are acting on the ball. And again, all the action and reaction pairs. So 2 parts to this problem. You're holding the ball, you've dropped the ball. You're holding the ball, what are the forces? And what are the action-reaction pairs? You drop the ball, what are the forces? What are the action-reaction pairs? So a simple question. Okay, so in this slide, I'm answering what are the forces on the ball when the ball is held. Let me get my pen going again. So here the ball is held. And in yellow here, this is meant to be my hand. And in blue here, this is the ball. And we're going to focus on the forces on the ball to begin with. And there are 2 forces. Here's one of them. It's the force of gravity pulling the ball downwards. And that force of gravity is due to the Earth's force on the ball. And so I've given that force this complicated subscript to it because I wanted to be clear that this force indicated by this magenta arrow is the force of gravity downwards that's exerted by the Earth on the ball. So that's one force the ball experiences. Second force, that's the force of my hand on the ball. It's what we call the contact force, or what we often call the normal force. That normal here just means contact force in this context. And so again, I've drawn that force. It's this force arrow. And when I've written the force, I've written it in this complicated subscript way where I'm saying it's a contact or a normal force of my hand that's acting on the ball. And so those 2 force arrows are the 2 forces that act on the ball. This magenta one downwards, this orange, horrible orange one upwards. And actually in this situation where you're holding the ball, those 2 forces are equal sized, oppositely directed. And that makes the net force, the total force, the sum of those forces 0. And so the ball is just sitting in your hand. So those are the 2 forces that are acting on the ball. Now, each of those 2 forces has a partner, an action-reaction pair. They are not partners, action and reaction pairs. They're different types of forces. One's a contact force, one's a gravitational force. They're due to different external influences. One's due to the Earth, one's due to my hand. So it's important, they're not action-reaction pairs, although they are equal and opposite. The action and reaction pairs are the following. So the force of gravity of the Earth on the ball, the action and reaction pair to that is the force of gravity of the ball on the Earth. So the ball is pulling the Earth up as strongly as the Earth is pulling the ball downwards. It's remarkable, fantastic to think of that, I think. Likewise, the partner, the action-reaction partner for my hand's force on the ball is the ball's force on the hand. So the ball exerts a contact force or a normal force on my hand. And so that's the action-reaction pair for my hand's force on the ball. And so you can see I've labeled those action-reaction pair forces appropriately. This one down here is force of gravity, and is the ball exerting a force of gravity on the earth, pulling the earth up. This one over here is the contact, a normal force, and it's the contact force of the ball exerting a force on my hand. So that's the situation with the ball in your hand. Now let's drop the ball. I often drop the ball, and let's drop the ball. If I can. If I can get to the slide in which I drop the ball. Okay, ball falling. So now the ball has left the hand and it's just falling towards the ground. So what are the forces here, and what are the action-reaction pairs here? Well, in this case now, the only force that's acting on the ball, oh crap. Here we are, sorry. Oh gosh. The only force that's acting on the ball is the force of gravity. It was there when the ball was in my hand, and it's still there when the ball is falling. The force of my hand has gone away because I'm no longer holding the ball, but the force of gravity hasn't gone away. So gravity, the earth is still pulling the ball down with the force of gravity. Now this is interesting now. When I was holding the ball, there was this perfect balance between my contact force and the gravitational force. That meant that the net force was 0 and the ball stayed in my hand. But now my contact force has gone away. There's still the gravitational force, though that I've got a net force on the ball. It's due to the gravitational force. I've tried to indicate that over here. There's now a non-zero net force or total force or some force. It's equal to this exposed gravitational force. And because it's not 0, there's going to be a change in motion. The ball is now accelerating towards the earth. And so that's what's happening now with the ball falling. That force of gravity on the ball has an action and reaction partner. It's down here, downstairs here. It's the force of gravity exerted by the ball on the earth. And so there's actually now a net force on the earth as well. And that net force on the earth is due to the gravitational force of the ball acting on the earth. And so not only is this is interesting to think about, not only is the ball accelerating downwards due to the pull of the earth, but the earth is accelerating upwards due to the pull of the ball. Now, the ball doesn't have much mass, so the acceleration is large because it has little inertia. The earth really has a lot of mass. So the acceleration of the earth upwards is much, 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 much smaller because it's so massive. But they are both accelerating towards each other. They're both exerting forces on each other. Oh, I didn't mean to do that. Well, that's okay. I've got a quiz question coming up, I think, in just a second. Let me go back and check that. I don't have a quiz question coming up. It's coming up in a few minutes, so I gotta cram it in, and I will do. I just wanted to make, before the quiz question, a couple of comments on mass and weight, because in our everyday language, we use kind of mass and weight to mean the same thing, but in physics language, we don't use mass and weight to mean the same thing. So in physics language, when we talk about mass, we talk about that as a measure of the amount of matter. So here's the mass of the apple. It's a measure of the amount of matter that the apple owns. It's a measure of the apple's inertia. When we talk about weight, on the other hand, in physics, we mean the force of gravity that's pulling on the object, pulling on the object, the apple. So there really are different things in physics. For example, one's a scalar, mass is a scalar, and weight, force of gravity, is a vector. And they're related, though. We'll use this relation a lot through the semester, but I'm just going to introduce it here. It comes from Newton's second law, and knowledge that the force of gravity produces the acceleration of gravity. The weight is related to the mass. The weight is equal to mass times the acceleration of gravity. So that's just like an F equals ma applied to the gravitational force. And so this shows you how mass on the right here and weight are quite different, and that weight is a force and mass is a measure of inertia. And just to illustrate this fact, what we're going to do on the next slide is imagine that we got a 1 kilogram apple. I think that's a big apple, isn't it? We're going to figure out its weight. We're going to figure out its weight on Earth, on the moon, and also on Jupiter. So let's do that quickly, because I've got to cram in the quiz. So I've got to do this in 1 minute. Okay, so let's figure out the weight of apple on Earth, moon, and Jupiter. And let's do it really fast. Talk really fast here. Okay, so on Earth, the weight of the apple is the mass of the apple times the acceleration of gravity on Earth. I put a little e here because we want the gravity on Earth. So I'm going to take the 1 kilogram mass, I'm going to multiply it by the 9.8 meters per second squared. I get 9.8 newtons. That is the weight of the apple near the surface of the Earth. What about on the moon? I take the apple to the moon. What's the weight on the moon? It's the mass of the apple times the acceleration of gravity on the moon. You probably know that the acceleration of gravity on the moon is about 1/6 of the acceleration of gravity on Earth. So 1 kilogram times the 1.6 meters per second squared acceleration of gravity on the moon gives you the apple's weight on the moon. It's only 1.6 newtons, much small. It's much smaller mass. On Jupiter, you probably know that Jupiter's one big heavy planet, and it has one big strong pull of gravity. And so the weight of the apple on Jupiter is, again, the mass of the apple times the acceleration of gravity on Jupiter. So it's 1 kilogram times the acceleration of gravity on Jupiter. The captioning is now covering up the number, which I don't remember, for the acceleration of gravity on Jupiter, but here's 26 newtons. That's the force. That's the resulting weight of the apple on Jupiter. So apple weighs very different things on Jupiter, Earth, and the moon, and on the sun. Its mass, however, on all those stellar bodies is always the same. Let me just say that next week, we've now introduced the laws of motion, Newton's 3 laws of motion. In the next classes, the next 2 classes, we're going to be applying the laws of motion, looking at illustrations of the laws of motion, looking at examples of the laws of motion, and meeting some common everyday forces like gravitational force, like tension force, and other forces. So we're going to be discussing those. So I'm going to move over to question time.